Hello, I'm Tuesday Cabang. My project was understanding the LEE, or low energy enhancement, of heavy elements by constraining nuclear input. I worked with Dr. Artemis Spiro at Michigan State University. Unfortunately, I couldn't go there, as I don't think anybody could. But it was my first experience with nuclear physics, so it was really interesting. Um, Before I explain this graphic, I'm going to explain what an isotope is for anyone who doesn't know. An isotope is any form of a chemical element that has the same number of protons but a different number of neutrons. And this is essential for creating the elements, as you can see here, after stellar burning, after iron, neutron capture processes are needed to create the rest of the elements on the periodic table. As seen here, this is a chart of abundance versus atomic mass number. You can see how there's abundances of different elements created in different stellar environments. So after stellar burning and iron, after that, depending on the environment, whether it's a neutron star merger or a supernova or something like that, the rest of the elements are created. Okay, so for the abundances, we have the S process, which is about 10 to the 8th neutrons per cubic centimeter in density, and the R process, which is the 10 to the 20th neutrons per cubic centimeter in density. And the I process is a recently proposed as the abundances, as you can see here. If it was either the S process or the R process, the abundances would be distributed along this line. But as according to measurements and observations, we have a whole swirl of other abundances popping up in the graphics here. The I process is around 10 to the 15th neutrons per cubic centimeter, and it's needed to explain these weird abundances. The I process runs along the isotopic chain really close to stable isotopes, and it's well constrained because of how close it is to stability. But the only property that we don't know in detail is the neutron capture reaction rates. As seen here, this is just a visualization of a neutron capture. So let's say a supernova happens and a bunch of neutrons hit a nucleus. And once the neutron hits a nucleus, it de-excites all the way down to its ground state. And while it's going through these little steps, I like to call them steps, as it's going through these little steps, it releases gamma rays here. And in recent years, around in the past 10 years, according to recent measurements and observations, a distinct increase in the gamma ray strength function, if we plot it as gamma ray versus energies. Usually it's expected to be a bell curve, but in lower energies, there's actually been an increase, and we have no idea why. The nature of this is unknown. We don't know whether it's electric or magnetic, and it's unexplained. This is another. This is a sample plot that shows the upend in this circle here. It's expected to go down in this natural bell curve, but in recent years, it's been showing an increase in lower energies here, as you can see. Okay, so I first off, I had to get used to all of the lingo and jargon, but I used Talus, which is an open source software package that you can use to run measurements, run nuclear reactions, and get data to plot them. And I also used Spider to plot all of these measurements. I initially focused on niobium 93 to 94, and that was just a sample nucleus just for me to get used to the data and how to work in altering parameters. Then I shifted to barium and gamma reactions from barium 141 through 146. So I worked from 141 to 142, 142 to 143, all the way up to 146, just to see if there was an impact on whether it was an odd number of neutrons or protons, to see if there was an effect. Lastly, I shifted to samarium to study, to compare this data to the University of Oslo, because there was actual observational data taken And we wanted to have a more realistic data set to compare it to. This was the first plot that I actually got. It shows a cross-section ratio from barium, 141 to 142, technically. This was me changing the parameters to see what the effect would be. So the red is no parameters as a control, and then I started changing the actual energy levels. And you can see that it was expected to change. It was expected to change the slope of it, but it's actually, you can see that it's not like a smooth linear slope. It actually has an energy dependence, which we did not expect. And this is what I was working on last. This is samarium 151, 152, and 153 to 154. And here I showed that I was comparing different parameters to get the closest to the Oslo data that we got. So the black is the Oslo data, and I was comparing different parameters to see which one was closest in order to apply more realistic parameters. The next step would have been to apply an upend to see what those what the effect of the upend had on the cross sections, but time constraints didn't get me there in time. In conclusion, the I process is a newly proposed neutron capture process, and it explains certain abundances within heavy nucleosynthesis. The gamma strength function is an ingredient that we need to pay attention to, as this low energy enhancement has popped up in recent measurements over the past 10 years. Including an LEE in experimental data has shown an effect, and it is energy dependent, which could have an effect on astrophysical calculations as far as abundances. And future plans are to have further projects with different isotopic nuclei to compare it also with the University of Oslo data. And thank you.
I just had a question. I think I missed it. What LEE stands for? Could you re-say what that actually means?
Oh, okay.
Yeah.
LEE is a technical term for low energy enhancement, which is an upend as seen. Oh, let me switch slowly. There we go. This is a technical term for the upend seen in the slope here, the bell curve. It stands for low energy enhancement.
Okay. Low energy. Okay. All right. Thank you. And go ahead, Andrew.
So Tuesday, nice talk. I wanted to ask about the next to last slide that you showed with the results for samarium. Yes. And I was just wondering about the Oslo data that are plotted there. I mean, they show kind of, they're not in a perfect straight line, right? There's kind of some bumps and wiggles there. Is that something like, are the bumps and wiggles, are those like, you know, real features that you know, we should want to try to explain, or are those just sort of, you know, fluctuations in the measurement of some sort that we don't really care about?
Those are natural fluctuations. None of the data from the University of Oslo is a perfect linear plot. There is some variation in the measurements, and it's all about the accuracy of the instruments involved. And as seen here, especially in samarium 153, the variations are a lot. Yeah. The dotted line is, well, as a line of best fit, it was just for me to compare the data. We'll compare the parameters for the closest match. The fluctuations are natural, and I don't think we need to pay too much attention to that.
Okay, thank you.
Well, it looks like that is all the questions that you have. Great job, Casey, and great job, Tuesday. Can we give our speakers a round of applause one more time?